7.5 is our second to last section. We're going to be working on what we call complex fractions. So basically our objective for today is very singular, just one thing. We want to learn how to simplify these complex fractions down into being the simplest, most reduced fraction we can. So if you wanted to describe these using, I think some pretty good descriptors, I would say that these are fractions within fractions. And how do we break these down and get them simplified? Guys, I'm not going to mess around. I'm not going to show you like the difficult way and then show you the easy way. I'm going to show you the easy way. Make sense?
Yes. So we don't have to learn the difficult way.
There's no reason to. It's just an algorithm to be able to simplify it. So here's what it is. If anybody is like, whoa, how does that work? Why does that work? I think it is relatively clear, but if you want, I can show you the longer, more difficult way, which might explain a little bit as to how this works. Okay? So here's what we do. I want you guys to take a look at number 1. It says simplify completely. And with this, you can see that there's in there pretty clearly a fraction within a fraction.
Yeah, but doesn't it really not mean fraction?
So, Grace, let me just finish my explanation real quick. So would it be fair to say that, I'm going to highlight this in purple, can you guys agree that that's like the main fraction bar? Okay, the main fraction bar is right there. And then what I am highlighting in red, I think we could call that the numerator. And then what I'm highlighting in blue, I think we call that the denominator. So when I say these are going to be fractions within fractions, does this make sense?
Yes.
Grace, does this answer your question?
No.
What was your question?
Oh, mine wasn't a question. It was a statement.
What was your statement?
That isn't that just the same as like the top one divided by the bottom one?
Yeah,
Yeah.
exactly it. Okay, so I will say this. I hope you're listening. That you could do this an alternative way, and somebody might debate whether that alternative way is easier than what I'm about to show you. I would argue with that, but maybe some of the upcoming examples, I don't think there would be an argument. So here's what we're going to do with this. The reason why we just practiced what we practiced is we are going to look at the denominators within each fraction. So in other words, I would say the 5 is a denominator. And what's the other denominator within the smaller fractions? The 15. Jake? So here's what we're going to do. We're going to look at those two numbers, those two denominators, the 5 and the 15, and we're going to find the least common multiple of them, right? Just like we were practicing. So what is the least common
15.
multiple of 5 and 15?
15.
Right?
Grace.
Least common, are you guys with Grace on that? She got a lot of enthusiasm, some volume. She's right. Least common multiple is 15. Now here's what we're going to do with that. But wait a minute, I'm looking, Luke, you good with that 15? Yep. You're good? Okay. Here's what we're going to do with it. We are going to take that 15, and we are going to multiply the top fraction by 15, and we're going to multiply the bottom fraction by 15. So it's going to look like this, times 15 times 15. And if you recall what we've been doing with these rational expressions, you are definitely allowed to multiply the numerator by something as long as you multiply the denominator by the same thing, right? So that's all I'm doing. I'm just multiplying the top by 15 and the bottom by 15. And let's think about, bless you, what's going to happen here. When we've multiplied these rational expressions in the past, we've tried to simplify them. Do you guys see how the 15 and the 5 will reduce?
Yeah.
How will they reduce?
3.
3 and 1. And then, wouldn't the 15 and the 15 reduce down to just being 1s? That's right. So 1 and 1. So to finish this one off, let's remember the way that we multiply fractions together is we multiply the numerators together. So let's go with that. What is 12x squared times 3?
36x squared.
36x squared. And now, hey, listen. Denominators now, what's 1 times 1?
1.
So division by 1 really makes no difference, does it?
No.
So I'm not even going to bother writing that.
No.
The main fraction bar is there. Now down in the denominator, I'm going to multiply the 7x times the 1, which of course is just 7x. I just heard a wait.
Okay.
Do you see it?
Yeah, I got it.
Okay. And then, of course, 1 times 1 is 1. So I'm not going to bother writing 7x over 1. So then once you've done this, you want to do one last final glance and ask yourself, no, we've simplified it significantly, right? No longer is it a fraction over a fraction. It's just a simple fraction. We want to do one final glance and ask ourselves, is there any further simplification that could be done? What do you see? The x's, right? Isn't the top factored? It's 36 times x squared. The bottom is factored 7 times x. So you could actually use those old chapter 5 rules. If you are dividing a base by a base, what do you do with your exponents?
Add them.
No.
I mean, sorry, I meant subtract. Sorry.
Subtract and you write the result in the numerator. That would be one way of looking at this. You'd end up with 36x over 7 when you reduce those. So that last step is nothing new. The first step definitely is. If you multiply by the least common multiple of the denominators, that's going to get rid of all the fraction over fraction stuff and get you to something that's a lot more simple, something you can probably reduce pretty quickly. Make sense? Okay. I think we'll do one more. Maybe 2 more. We'll see. Okay. So let's take a look here at number 2. You see number 2? This is going to be where this strategy that I'm trying to teach you guys is going to be really, really important. Do you guys see that you've got a fraction in which the numerator is this in red? Like that whole thing is the numerator.
Yes.
And then this whole thing down here is the denominator. So this fraction is even more complicated than the other one. But we can make it just as simple as the other one, maybe even simpler, by doing this step first, asking ourselves, what is the least common multiple of the denominators? So specifically of these numbers. So you look at your denominators only. There's 4 of them this time instead of 2. Ask yourself, what is the least common multiple of 5, 9, 3, and 5? So don't just shout it out. Think it over for a second. What do you... Yeah, write it down. What do you think the least common multiple is? Just like we were doing at the start of class. Least common multiple of 5, 9, 3, and 5. So it looks like to me, so what you're doing, this is the long way, right? So getting a common denominator and adding, common denominator and adding, then flip and multiply, that's not a bad way. It's just the longer way. I think you're going to find that my way is a little faster. Your way is not bad, though. Okay, what did you guys come up with? What's the least common multiple? 45. So here's what we're going to do. We are going to take that least common multiple, and we are going to multiply the numerator and the denominator by that. So I'm going to put this in parentheses and write times 45. I'll put this in parentheses and write times 45. Good? So check this out. What property needs to be used to properly multiply this? Distributive, yeah. So I'm going to multiply 45 over 1 times 2 over 5. Let's think this over. What's 45 times 2? 90. And what's 5 times 1? 5. I'm going to do this part here. 45 times 1, of course. 45. 9 times 1 is 9. Are you noticing that you probably could do this in your head? Are you noticing that these are going to reduce? Really, really nicely. Take a look at the distributive property in the denominator. 45 times 1 is 45. 3 times 1 is 3. And then same kind of thing here. Plus 45 times 1 is 45. 5 times 1 is 5.
Yes.
Now, if you can just reduce these, it's going to boil down to some pretty simple arithmetic. What's 90 divided by 5?
18.
Yep. What's 45 divided by 9?
5.
What's 45 divided by 3?
15.
And 45 divided by 5?
9.
This just got a lot simpler really fast. So then 18 minus 5 is 13. 15 plus 9 is 24. And you're done. The key, as you can probably see, is finding that least common multiple and appropriately applying it. Question?
At the beginning, why'd you just make the basis 45? Why'd you distribute?
So you're suggesting the longer route. You're suggesting why not get a common denominator, adjust your numerators and add, and then do the same thing in the bottom, and then go copy dot flop and reduce. That's the longer route. That way works. I think you're going to find, especially when you start getting x's in these, that is going to be a significantly longer route, but it works. So if you look at that and you're like, nope, I'd rather do it that way, I got no problem with that. So the original answer to your question, you said, why didn't you just do what you suggested? I think this way's faster. That's basically the long and short of it. Yes, ma'am.
So at the beginning, couldn't you have just crossed out the 45 and the 9 and like reduced it before you multiplied?
Yes, you certainly could have. And so that's why I referenced that a little bit. What I was thinking was, as you're going from this step to this step, if you can just do 90 divided by 5, or if you can cancel the 45 and the 5 and get a 9 times 2 is 18, if you can do that, do it. So I really think this step right here is completely unnecessary. If you can do those cancellations and multiplications in your head correctly, do it. So that'd make it even faster. So I'm fine with that, definitely. Okay, anybody else? Okay, let's see if you're ready for this one. This might be where we finish today. Let's see how it goes. Take a look at number 3. I think number 3 has some x's in there. It does. Let's make sure we all get the right least common multiple, then I'll let you guys try to mess around with this and see how it goes. Your denominators are 5x, 3, and x. What do you guys think the least common multiple is?
15x.
15x. See if you guys can use that 15x to then simplify this fraction completely. Ready, go. Right. So what I'm going to do is I'm going to write this out as the top multiplied by 15x, and I always put that over 1, and I'm going to multiply the denominator fractions by 15x over 1 as well. Make sense? Consistent at least? Okay. So now what I'm going to do is the distributive property like we did before. So I'm going to multiply here. 15x times x is 15x squared. 1 times 5 is 5. There's my main fraction bar right there. Then this multiplication here, 3 times 15 is 45, so you have 45x. 1 times x is x. So that's that distributive property in the top. Any questions so far? Look at what you have. Look at what I have. Okay. So then down here, same thing. 15x times 1 is just 15x, and 1 times 3 is 3. And then lastly, we have plus, and the 15x multiplied by 2 is 30x, and 1 times x is x. All right, now once you've done this, you want to look at all the fractions, all 4 fractions, and all 4 of them should have some type of reducing, right? All 4 of them. So all I'm going to do, let me explain what I'm not going to do. As I walked around, I want you guys to see this. As I walked around, there's a pretty healthy number of people that tried to cancel with this and this. Do you understand why that's wrong? What's the symbol that tells you that you should not be doing that? Subtracting, the minus sign. You cannot cross-cancel minuses or pluses. You can with multiplication, but that's not what we're doing here. So I would say this first fraction, 15x squared over 5, would reduce down to be 3x squared, right? Because 15 over 5 is 3. The x squared doesn't have anything to cancel with. I'm looking at this one right here. 15 over 5, yeah?
Yep.
Okay. And then 45x over x, the x's would cancel, leaving me with minus 45. And then down here, lower left, 15 over 3 is 5. There's nothing for the x to cancel with. And then 30x over x, the x's cancel, leaving me with 30. And you can see now, instead of having a fraction within a fraction, don't I just have a fraction? So that's really good progress. And maybe I'm done. What I need to do to finish this off is I need to look at the numerator and the denominator and ask myself, is there anything else I could cancel? And to do that, what do I need to do first? Factor, right? If you're thinking about canceling, you need to have factors first. So what can I factor out of the top? 3 comes out. What's left over?
X squared minus 15.
Got it? Yep. And what comes out of the denominator? And what's left over? 6. So now that we're fully factored here, now you can pretty clearly see if something cancels out or not. What do you guys see? What cancels out? Nothing. Nothing cancels out. There are no like factors that cancel out. And so we could go back here and we could say that that's our answer. Although if you wanted to say that was your answer, either one of those would be perfectly acceptable. No problems at all. Jake?
So you couldn't take the x out of the 1x out of the 3x squared and x out of the 5.
No. Okay, so if you look at, when you said take them out, are you talking about,
Like just factor them.
are you talking about this?
Yeah. Just
Can't-
take like just so it's 3x.
Yeah, like factor them out.
Like
Well,
just
so here's the
factor out
thing.
1x.
So, okay, fair enough. You sort of could. Here's the problem. When you look at the numerator, do both terms have an x?
No.
So you really can't.
Why?
So if I factor out an x, I'll just look at the numerator here. If I factor out an x, you're telling me what would be left over?
9.
Sorry?
3 to the second power.
Oh, no, okay. So here, let's,
So I thought like
so you're thinking that like that squared would just sort of hover and then like attach onto the 3?
no.
So why would it be 3
So
squared?
I know it's like 3 times x.
Yep.
So I was just, and then in the denominator it's 5 times x. I thought you could just take out one of the x's.
You still haven't factored, you keep saying take out, and you haven't factored anything, right? So if you did this, if you said x squared is really x times x, and of course 5x is really 5 times x, I think this is what you're saying, and now do this and this,
Yeah.
you can't do that, and here's why. The numerator is still a subtraction problem. You have not factored the numerator. Now, you have factored one of the terms in the numerator, I'll give you that, but you have not factored the numerator at all. You haven't factored the denominator at all either, because the denominator is still a plus, an addition problem.
That's why you factor out 3x and like 5x.
So, okay, so Grace, this is what I thought you guys were going for, and we're going to have to close this up pretty quick here, so we have time to do our quiz. So let's just look at the numerator. If I factored a 3x out of the numerator, tell me what's left over.
X minus 15.
Okay. Are you guys paying attention? Some of these same questions might like come drifting across your mind in the middle of a quiz, so I think it's good for you to think about this now. Grace has proposed this. Now, shouldn't I be able to redistribute this and get the same thing I started with? So if I do that, what is 3x times x?
9x squared.
No, 3x squared.
Just kidding. I was just kidding, guys.
You're good. So that seems to match, right?
Yep.
But what about this? What's 3x times minus 15?
Negative 45x.
And that does not match.
Okay.
Did you see how the 45 did not have an x to begin with?
Yeah.
So in order to factor out an x, like you're suggesting, all the terms in the numerator have to have an x.
Yeah.
And they don't, so you can't.
Yeah.
Okay. Hey guys, I hope the rest of you guys see the value in what we've been talking about here for the last couple of minutes, which Jake wants to continue doing. Go.
So, but like back in the first one,
Okay, what do you mean by the first one?
first problem we did today.
Did you notice that those were all monomials?
That's the
That
one.
makes it look different.
Yeah, so that's the reason why you could take the x out
Because
of the monomial.
the top is already factored, right? Notice the top is not 36 plus x squared.
Yeah.
It's 36 times x squared. And so perhaps a really fundamental thing that's really important to understand coming out of an algebra class is there is a totally different meaning between these two expressions. Yet sometimes we seem to think they're the same. One of them is multiplication, the other one's addition, so they each have their own implications. If you have this, you can absolutely cancel this with this and just get an
Yeah.
x to the first in the top because the top is factored. It's a multiplication problem. If you have this, you absolutely cannot do anything with this because the top is not factored. Over here, the top is factored because it's a multiplication problem. Over here, the top is not factored because it's an addition problem. So that's like the fundamental difference here, times versus plus.
But it's like the 36x squared is like the same thing as 3x squared.
Yeah.
Yeah,
Same-
and it's
same-
minus 45, so that makes it so you can't do it.
No, but so what you're doing is you're picking out parts of the numerator. Like when you look at 36x squared over x. When you look at the numerator as a whole, not little bits of it, but like the entire thing is factored. When you look at this entire numerator, the entire numerator is not factored. Like, sure, this, if you looked at just this little part of it, you could say, yep, that's something times something. I get it. But you're not looking at the numerator when you look at that. You're looking at a little part of the numerator. When I say the numerator has to be factored, I mean the whole numerator. And right now, because it's a subtraction problem, the whole numerator is not factored.
Good.
That make sense? Be careful about picking out little pieces. Here's another good example. This is parallel to what you're talking about. If you had, this is a whole different question. Oops. If you had like x squared plus x squared plus 3x plus 2 over x plus 1, there's always a temptation to be like, oh, cool, boom, boom, right? But look at the numerator as a whole. Here's the entire numerator. Is the entire numerator factored? No, right? It's a plus, it's an addition problem. And so you cannot do this. If, however, you decided, I'm going to actually try to factor this, and you realize that the numerator is really x plus 2 times x plus 1 over x plus 1, you can now look at the numerator and decide, hey, you know what? The entire numerator as a whole is factored because it's something times something. Now you're allowed to cancel out whole factors. So you could cancel this with this. You see the difference? Okay, cool. All right, let's make this quick. Jake and Luke, you need to exit. I believe everybody else can stay.